So I'm calling this session the truth, well, sort of, about transistors, and we'll look at what transistor characteristics really are, not in terms of nullators and narrators, but as more realistic models. Um, to start that, we'll first look at a diode. So if you have a diode with the two terminals, I'm just going to call it B and E. So the voltage VBE is the voltage across the diode, and the current through the diode, I'm going to call it ID. So if I draw a plot of the voltage, which is in the x direction, which I'm going to call VBE, current, which I'm calling ID, which I'm going to draw in the y direction, then the equation is actually ID is a very small current called I0 scaled by e to the power of, well, I should have started a bracket, VB by VT minus 1. And yes, this VT is the familiar thermal voltage, which is KT by Q, which is around 25 millivolts at room temperature. So what you get is that initially the current is very small, but then after some voltage it actually starts blowing up exponentially, and usually this voltage is around 0.6 volts. Well, I should have put that in blue, but okay. Okay, so there, I put it in blue. So it's 0.6 volts, and after that the current actually is fairly large, and to change the current from this value to another value, like even if order of magnitude, like changing by a factor of 10, maybe 0.1 volt or something, maybe just 100 millivolts. So a very small change in voltage at that point can produce a very large change in the current. So I'm actually just going to derive it. So I'm going to look at if I take a derivative of the current as a function of the voltage, then I get that I'm taking a derivative of this with respect to this with respect to VBE, and I get I0 by VT into e to the power of VB by VT. Okay, so what this if I look at this, when the current is large, the exponent part is very large compared to 1, so this is basically almost the same as ID. So this is ID by VT, and this has dimensions of current by voltage, which is basically the dimensions of 1 over R, or in the case 1 over R of E. So which is why we have been using RE is equal to VT by ID, basically VT by I. Now how does this connect with the bipolar transistor? Well, the bipolar transistor, the arrow actually indicates a diode. that also is a diode, but in an NPN, which is what this is. This reflects P-type material, this is N-type material, this is your P-type material, and this side is your N-type material. So this is actually a diode, and we have been forward biasing a diode carefully, but we have been forward biasing a diode. So this was the P and this was the N, and this voltage is why we are saying that this is around 0.6 volts or 0.7 volts, and there's actually another diode this way. You can't put diodes back to back and get a transistor. There is something a little more than that happening at what you call the base, which makes it act in a special way. But we are reverse biasing this diode, so this voltage is usually higher than this voltage, and this voltage is usually higher than this voltage, and then you are in a normal functioning mode of a transistor. If both the diodes are forward biased, you are not in the normal mode of functioning of a transistor. So this is the base, this is the emitter, and that's a collector. So just so we remember, the base is always higher than the emitter if it's functioning in the normal way, and same way the collector, where in a bipolar transistor it can be just above the base, and that's enough. This will be 0.6 or 0.7 volts. This doesn't need to be that high. In fact, some transistors will work all the way down to this voltage being even 0.4 volt. It's okay, but it's best to basically keep this at least to about 0.6 volts. Okay, so far I have explained the forward current that's going to base to emitter, and how the change looks sort of like a 1 over resistance, which is this, which is why in our model we've been using a resistor. The only thing I have left to explain is the narrator sort of equivalent that we have. Okay, so let's see if I can give some sort of a hand wavy explanation for what actually happens. So the current goes from P to N, but as you know, electrons have a negative charge, so the electrons travel in the opposite direction. So the electron is being shot from the N to the P. I'm forward biasing, it has a fairly large amount of energy, and it just shoots from N to P across a barrier that's there. Never mind if you don't know the barrier. What happens is that most of these electrons, in a more realistic, I have just shown NPN, in an even more realistic transistor, you have a fairly large collector area, maybe even a smaller emitter area, and you have a really thin base area. It's just that thin. That's your P. So the electron that's being shot through mostly makes it out to the collector. So most of the emitter electrons make it to the collector. So most of the emitter current makes it to the collector, and a small amount of emitter current recombines with holes in the P. P has holes, this has electrons. It recombines and creates a current here. But if there was no recombination, there would be no shoot through either, right? So not right, but that's how it is. So I need to have a small base current. This is my base, so this is the base current, and then my collector current can be a large value. So the model sort of a bipolar transistor is that you have a diode, equivalent, but whatever current comes here, whatever is this current, most of that current is being driven by what is called a current controlled current source. So this is some emitter current, So most of that current is coming from the collector. So, well, where beta is a large number. Oh, actually, for an NPN, this is not correct. So this current is even larger than this, and oh no, I got it right the first time, sorry. I was right. So beta divided, it's slightly smaller than the emitter current, and the one that's left is the base current. The base current is IE by beta plus 1. So the total beta plus 1 divided by beta plus 1 becomes just I. So this is one model of a fairly accurate model of a bipolar transistor, which respects the fact that it actually has a nonlinear device and a diode and the forward bias, but most of that current is actually coming somehow from the collector. Another model that's fairly common basically looks at the base current. So if I assume there is a base current IB, then this model basically refers everything to the base current. So there is a current source, it's still the same, but it's basically just talking about that it's beta times IB, and then your sort of emitter current is an expression of that in terms of 1 plus beta times IB. Okay, so these are two fairly common models that I used. One which basically refers everything to the emitter current and says most of the emitter current is coming from the collector and a small amount comes from the base. The other says there is a small current in the base and the collector current is beta times larger than the base current, and then the emitter current is the sum of the two. This beta factor in some multimeters is also called HFE. So when you're measuring HFE, you're measuring how much is the gain in the collector with respect to the base current. So far we had not looked at the base current at all. We had just put an allator there, so there was no base current. But in reality, in these bipolar junction transistors, you will have a small base current, and you will scale that by a larger number, usually like 200 or something like that. So you don't really notice it because we only worked up to a gain of around 100. So we didn't really notice that there needed to be a large base current for that to happen.